In 2018, a scale model of the J-20 stealth fighter was placed in the American Air Dominance Center at Savannah Hilton Head International Airport in Georgia, USA. This center is the main base for the air combat training of the fourth-generation fighter jets of the U.S. Air National Guard, indicating that the United States has begun to seriously study how to deal with the J-20 fighter. This article is referenced from the article US F-22 Raptor Stealth Fighter vs. Chinese J-20 Stealth Fighter. Who will win? In the American magazine The National Interest after the 1980s. Beyond visual range air combat has become the main style of air combat. For this reason, the U.S. Air Force has developed the F-22 fighter with stealth ability, supersonic cruise ability, super maneuverability, and advanced integrated avionics system. Among them, the most core technical advantage is radar stealth performance. Radar waves are electromagnetic waves that propagate in a straight line and can be reflected, refracted and diffracted. When irradiating an aircraft, they will be directly reflected back. The F-22 fighter first modifies its shape and changes the fuselage angle, such as a diamond-shaped nose, inclined twin vertical tails, and swept wings, to reflect electromagnetic waves in unimportant directions. However, the edges will generate diffraction of electromagnetic waves. For this reason, the F-22 fighter uses integral skin technology, jagged hatch openings, parallel wing and tail leading and trailing edges and air inlets to eliminate these diffractions, and also uses a hidden air inlet to eliminate cavity scattering of radar waves. However, modifying the shape only reflects radar waves from one direction to another. In this direction, the reflected direction of stealth forms a peak value. This peak value can be alleviated by stealth coating and concentrated in several small angle directions through shape design. Unless the radar is exactly irradiated at this angle, changing the flight attitude and heading will also become a transient peak signal. After a series of stealth designs, the nose cross-sectional area of the F-22 fighter in the centimeter band is 0.02 to 0.003 square meters. And in the decimeter wave band it is 0.1 to 1 square meter, while the F-15 fighter is as high as 12 square meters. And the smaller F-16 fighter also has 3 to 5 square meters. The radar stealth standard is measured by radar cross-section. The larger the area, the stronger the electromagnetic wave power scattered back to the radar direction, and the easier it is to be detected by the radar at present. Airborne fire control radars are all in the centimeter band. The detection distance for a 5 square meter target is 120 to 150 kilometers. And the tracking distance is 80 to 100 kilometers. The radar positioning system of the F-22 fighter is very accurate. It can approach the target quietly without turning on the radar and exposing itself to the opponent. Then, after using the phased array radar to emit a narrow beam that is not easily detected by radar reconnaissance equipment, it quickly inputs various elements for the missile. Then the AIM-120C missile is launched. When the missile enters the 20-kilometer autonomous guidance stage, it leaves the threat area with a supersonic cruise capability of 1.5 times the speed of sound. The enemy pilot cannot even see a spot on the screen before the F-22 fighter fires. Even if it is captured by the radar, it is automatically filtered out as a bird due to the too small reflected signal. And the radar of the F-22 fighter can disperse the radar signal over a wide frequency band and turn on and off instantaneously. So it is difficult for the opponent's radar positioning system to detect it when the enemy fighter's radar detects the F-22 fighter. The F-22 fighter has already opened fire. When the enemy fighter can lock onto the F-22 fighter, the AIM-120C missile has already flown in front. If the missile misses, the two sides enter within visual range air combat. The super maneuverability of the F-22 fighter, combined with the AIM-9X missile and helmet-mounted sight, can also gain an advantage in within visual range air combat. The Red Flag military exercise of the U.S. Air Force proves that third-generation fighters such as the F-15 and F-16 are very difficult to shoot down the F-22 fighter. But they suffer heavy losses themselves. The huge advantage of stealth is crucial for the U.S. military operating in East Asia, facing the Chinese Air Force with an absolute numerical advantage. The F-22 fighter can shoot down multiple Chinese fighters without any damage to itself. But this overwhelming technical advantage no longer exists after the Chinese J-20 stealth fighter came out. When the F-22 fighter made its first flight in 1997, the main equipment of the Chinese Air Force was a large number of J-6 and a small number of J-7 and J-8 fighters. Due to the huge technological gap, it was simply unable to compete with the F-22 fighter. Even the J-10 fighter, which is not as good as the F-16C fighter, had not been finalized. However, the J-20 fighter had been officially launched. After 14 years of development, it made its first flight in 2011 and was officially equipped with the Chinese Air Force in 2016. It is an outstanding example of an asymmetric technological strategic response to the F-22 fighter. The appearance of the J-20 fighter means that the United States is no longer the only country with stealth fighters. And the rules of the game will also change when the J-20 fighter was just undergoing flight tests. The U.S. military believed that the J-20 fighter is not a simple imitator of the F-22 fighter, but a hybrid of the F-22 fighter responsible for seizing air supremacy and the F-35 fighter responsible for system combat. Because the development of the J-20 fighter was completed after the 21st century, a series of technological and tactical changes of the F-35 fighter also affected the design of the J-20 fighter. Although the F-35 Joint Strike Fighter has unique advantages in avionics systems and other aspects, it pales in comparison with the J-20 stealth fighter in terms of maneuverability, stealth characteristics, and sensor capabilities. Using the F-35 fighter to confront the J-20 fighter will result in a very ugly exchange ratio. Only the F-22 a Raptor fighter, more precisely the enhanced F-22 fighter, can counter the J-20 fighter. However, the weaknesses of the J-20 fighter are that the unique canards, ventral fins, and nozzles will all affect stealth capabilities. The deflection of the canards during flight will lead to an increase in radar cross-section. The radar cross-section is different under different deflection angles. The diamond-shaped window of the photoelectric sensor below the nose of the J-20 fighter is about a dozen centimeters in size. In the face of L-band early warning radar, there will be a relatively large echo. These two aspects will make the radar cross-section of the J-20 fighter one order of magnitude higher than that of the F-22 fighter. The exposed tail nozzle and ventral fins are also major reflection sources. The ventral fins that sacrifice side stealth capabilities are to enhance flight stability and reduce the number and angle of canard trimming to ensure frontal stealth capabilities. The tail nozzle using the L-31F engine is almost non-stealthy. This is also inevitable. This gives the F-22 fighter a 1.76 times advantage in radar detection range. The F-22 fighter is equipped within a PG-77 active phased array radar, which has 2,200 6-inch gallium arsenide components. The 6-inch technology is in the hands of three companies: Sumitomo Electric of Japan, Freiburg of Germany, and AXT of the United States. Large-sized devices reduce signal processing noise, thereby increasing the detection range by 1.07 times. In 2002, the 46th Institute of China Electronics Technology Group Corporation and Zhongke Jingdian could only manufacture 4-inch ones. Therefore, the United States believes that the radar of the J-20 fighter has 856 gallium arsenide TR components. The peak power of the NAPG-77 active phased array radar is 20 kilowatts, which should be 1.18 times that of the J-20 fighter. And the detection range is 1.07 times. That is, the detection range of the J-20 fighter is between 187 and 227 kilometers, but both sides have stealth capabilities. So the radar detection range is greatly shortened. If according to the detection range difference of 1.07 times, the F-22 fighter can detect the J-20 fighter at 63 kilometers, while the J-20 fighter can only detect the F-22 fighter at 33 kilometers. If the F-22 fighter detects the J-20 fighter at 63 kilometers, then the range from 50 kilometers to 63 kilometers is its attack window. The internal bomb bay of the F-22 fighter can hold 6 AIM-120C-57 medium-range air-to-air missiles with a range of up to 120 kilometers, while the internal bomb bay of the J-20 fighter can only hold 4 PL-12 medium-range air-to-air missiles with a range of up to 70 kilometers. Neither in range nor firepower can it be basically equivalent to the F-22 fighter if both sides enter close combat. The F-22 fighter is equipped with a powerful F-119 engine and a vector propulsion device, and can move laterally and longitudinally at twice the speed of the F-16 fighter. The thrust vector nozzle can provide longitudinal control torque for post-stall maneuvers in a high angle of attack state. In close-range air combat against third-generation fighters, it has an absolute advantage in maneuverability. The Alabama 31F engine of the J-20 fighter is one level lower than the F-119 engine. Although the canards help improve maneuverability, they only improve controllability at high angles of attack rather than post-stall maneuverability. The F-22 fighter can first achieve nose turning to lock onto the fighter. However, the J-20 fighter adopts a unique aerodynamic layout of lifting body plus street rake plus canard plus fully movable vertical tail, which will provide very large positive lift and is very beneficial for exerting circling performance during high angle of attack maneuvers. The wing loading of the J-20 fighter is 340 kilograms per square meter, and that of the F-22 fighter is 370 kilograms per square meter. The circling performance of the F-22 fighter is not as good as that of the J-20 fighter. Moreover, the normal takeoff weight of the J-20 fighter is 4 tons lighter than that of the F-22 fighter, and the thrust gap is 60 kN. This is sufficient to offset the engine gap. If the F-22 fighter does not turn on the vector engine, the maneuverability of the two is basically on the same level. When at a high angle of attack, the lift-enhancing effect of the canard plus street rake of the J-20 fighter is very obvious. The F-22 fighter can only use the vector engine to increase lift, resulting in a relatively serious thrust loss, even if the F-22 fighter can lock onto the J-20 fighter first. If it enters a continuous dogfight, the J-20 fighter may gain an advantage, both adopt an integrated cockpit canopy, and the pilots have a very large field of vision. However, the J-20 fighter is large in size and has canards, so the visual dead angle is still larger than that of the F-22 fighter. At this time, the F-22 fighter will have an advantage. Both the F-22 fighter and the J-20 fighter carry to short-range combat missiles. The PL-10 and AIM-9X-3 short-range combat missiles are both 128x128 array staring focal plane infrared imaging seekers. The off-axis angle can reach 90 degrees, and the maneuvering overload exceeds 50 G. However, the diameter, length, drag, and weight of the PL-10 missile are all larger than those of the AIM-9X-3. Therefore, there is a certain gap in acceleration performance and turning performance. In addition, the F-22's infrared surface source jamming equipment can interfere with short-range combat missiles with infrared imaging guidance systems. The J-20 fighter has not found similar jamming equipment. The F-22's nozzle's infrared stealth treatment is also better than the tail nozzle without infrared stealth treatment. Therefore, the close-range combat performance is still better than that of the J-20. However, the J-20 fighter is divided into State A and State B. State A refers to the J-20 verification aircraft and prototypes before aircraft number 2017. The J-20 fighter of the verification aircraft and prototypes uses the Russian Alabama 31F engine. The maximum thrust is only 15 tons, and it cannot achieve super maneuverability and supersonic cruise. The 2001 verification aircraft only simply tests flight performance. The design of the 2002 verification aircraft has undergone major changes and is equipped with an active phased array radar. The 2011 prototype has modified the main wing, canard, air inlet, accelerator plate, ventral fin, and bomb bay, and added photoelectric detection equipment. The 2013 prototype has modified the height of the cockpit canopy. The 2017 is the last prototype. So far, all development work has ended. After aircraft number 2101, they are all mass-produced models in December 2016. 6 J-20 mass-produced aircraft numbered 78,271 to 78,276 were delivered to the Chinese Air Force and officially entered service in March 2017. In January 2018, actual combat training began. This model of the J-20 fighter uses the WS-10 engine. In 2023, the J-20 fighter using the WS-15 engine began flight tests. It is already different from what the Americans thought. The difficulty of canards affecting stealth has long been overcome. The canard of the J-20 fighter is the pinnacle design of the world's fighters. Chinese scientific and technological personnel have overcome many difficulties, such as the establishment of digital models and aerodynamic design after using composite materials for the canards, performing tip trimming, improving the control system, and applying absorbing materials. Even if the canards are deflected to 45 degrees, the reflection value is only between 0.01 and 0.001. The edge diffraction formed by the sharp edges is also between 0.0001 and 0.001. The absorbing material can also reduce by 5 to 10 decibels. The computer will also give a reasonable deflection angle according to the fuselage attitude, which has little impact on the stealth performance of the whole aircraft. If the photoelectric sensor window is ordinary glass, radar waves will penetrate in. But after coating a layer of steel tin metal film, it is sufficient to filter radar waves. This technology is the same as the cockpit stealth method. Due to early technical conditions, the cockpit of the F-22 fighter is stacked layer by layer. The first 3 prototypes of the J-20 fighter are the same, but the later ones are all integral formed, and the ability to prevent radar waves from penetrating is stronger than that of the F-22 fighter. The ventral fin is a unique design of the J-20 fighter, which can increase stability and the aerodynamic efficiency of high angle of attack maneuvers. The J-20 fighter after aircraft number 2016 completely covers the side of the tail nozzle with ventral fins and is coated with stealth materials, greatly reducing the side reflection value. The nozzle of the engine also has serrated trimming, expanding the outlet boundary, increasing the mixing of cooling airflow and high-temperature gas, and emitting radar waves to other angles, effectively suppressing X-band and Q-band radar waves. The engine air inlet is the place with the most obvious radar echoes on the fighter. The F-22 fighter's Garrett air inlet has multiple bleed valves and exhaust holes. The J-20 fighter's DSI air inlet cancels the boundary layer separation duct, bleed system and bypass system. It not only isolates the boundary layer airflow, but also shields the engine. The stealth effect is higher than that of the F-22 fighter, unlike the F-22 fighter, which needs to be coated with many layers of paint and is so thick that it sheds powder. The composite multi-element film used by the J-20 fighter weighs only 0.7 kilograms per square meter and can attenuate radar waves in the 8 to 40 GHz frequency band by 10 to 15 decibels. In 2015, a printed circuit board stealth coating appeared. The surface layer is a 0.8 mm FR for printed circuit board, and there is a 0.04 mm semiconductor and copper sheet below. After being energized, it can absorb 0.7 to 1.9 band microwaves. Below is a 7 mm honeycomb bottom plate. The total thickness is only 1/10 of that of American coatings, but it can reduce the reflectivity by 10 to 40 decibels, reducing the detection ability of the innate PG-77 active phased array radar from 3 kilometers to 6 kilometers. Moreover, it does not need maintenance and an air-conditioned hangar like the F-22 fighter after each flight. The 1475 active phased array radar of the J-20 fighter is the second-generation product in China's advanced avionics plan. The first-generation 98X project refers to the avionics architecture of the F-22 fighter and was later used on the J-10B fighter. The second-generation product is actually aimed at the avionics system of the F-35 fighter since 2002. It has a similar size to the innate PG-77 radar and has excellent low probability of interception. It can control the power of each radar beam and simultaneously emit hundreds to thousands of low-power radio waves of different frequencies, and then accumulate the radio waves of each frequency into one signal. The old radar warning device has no response to it at all. The radar's digital system also compiles the radio waves into pseudo-clutter that is different every time and completely blends into the background noise, so that the AL-90 for electronic reconnaissance system of the F-22 fighter cannot detect it either. Originally, it was thought that the detection range of the J-20 fighter's radar was 187 to 227 kilometers. However, the KLJ-7, a phased array radar developed by Nanjing No. 14 Institute for the Pakistani Air Force's FC-1 Xiaolong fighter has only 1,000 TR components, but its detection range is as high as 170 kilometers, even higher than the APG-81 radar of the F-35 fighter. It is still an export version with many reservations and a low price. The number of TRS of the 1475 active phased array radar has doubled, and gallium nitride material is still used. The power is doubled, and the detection range is at least 400 to 500 kilometers. The EOTS-86 photoelectric detection equipment of the J-20 fighter can detect point-like signals 150 kilometers away. With this system, the J-20 can detect and lock onto the F-22 fighter at a distance of 110 kilometers without turning on the radar, and then open fire first and leave after firing. The ability of the airborne computer determines how quickly a target can be locked on, how quickly a launch can be completed, and how accurate the ballistic calculation is. The airborne computer of the F-22 fighter is a product of the 1990s, with a processing capacity of 5 billion times per second. The airborne computer of the J-20 fighter is a product of the latter 10 years of the 21st century. Obviously, it has an advantage of later development. The AIM-120C-57 medium-range air-to-air missile has a range of 120 kilometers, and the acquisition range of the active radar seeker is 20 kilometers. For stealth fighters, it is reduced to 10 kilometers. Assuming it is launched at a distance of 100 kilometers and calculated at a speed of Mach 4, it must be continuously locked on for 51 seconds to reach the activation position of the active radar seeker. If it is launched at a distance of 60 kilometers, it must be continuously locked on for 30 seconds. Generally, if the continuous time exceeds 10 seconds, it may be detected by the electronic reconnaissance system of the J-20 fighter. So the advantage of the F-22 fighter is not prominent in terms of close-range air combat. If the J-20 fighter is equipped with the WS-15 engine, the previous instantaneous turning maneuver advantage of the F-22 fighter will no longer exist. The mass-produced J-20 fighter is also equipped with an integrated photoelectric detection system and a helmet-mounted integrated display and aiming system that the F-22 fighter does not have. The cockpit equipment is almost the same as that of the F-35 fighter. It did not follow the F-35 fighter to cancel the head-up display. Obviously, it does not want to encounter the difficulties of the F-35's heavy helmet, image delay, and night vision compatibility in close-range combat. The airborne photoelectric sensor can be used to obtain a larger field of vision than the F-22 fighter, a longer detection distance and more accurate target position parameters, making the F-22 lose the advantage of taking the initiative in close-range combat. In the face of a missile overload of 60 G, the super maneuverability of the F-22 will not be of much use when the J-20 fighter just appeared. There were indeed many deficiencies, but they were all within the expectations of the designers, and it was gradually upgraded to the full version step by step. The full version of the J-20 fighter overwhelms the F-22 fighter in terms of any performance. However, the F-22 fighter has not had any improvements in the past 20 years of service, and there are only 188 in number. Excluding crashed, tested, trained and reserve aircraft, there are actually only 126 in combat squadrons. If the serviceability rate of only 50% is added, the number of F-22 fighters that the U.S. Air Force can dispatch to the East Asian battlefield is less than 50. While the J-20 fighter of the Chinese Air Force is growing at a rate of 100 per year, all war zones have been refitted. Regardless of performance, the gap in quantity alone can overwhelm the U.S. Air Force.